Let me again emphasize the point. So when you look at this, you see these ups and downs every year. So obviously you feel the changes from year to year. This year has been a La Nina since the summer months, so gave some extra monsoon rainfall during August, September, and then is now colder than normal winter in parts of India, and there are also teleconnections of El Nino over the US, Europe, and so on. So those things happen. They're called natural variabilities and are related to just Earth's internal adjustments and feedbacks, right? Not necessarily to the human forcing. The question, of course, is how is human forcing or the anthropogenic change and global warming are affecting natural modes like El Nino and La Nina? Are they making them more intense, less intense, more frequent, less frequent, changing their patterns, and so on, which is a much more complicated issue, basically because we don't have enough observations to say them for sure, and the models give somewhat different answers based on their own biases. But what is striking is if you look at the change in temperatures decade by decade going into the 19th century, and as we saw, there were ups and downs before the 1940s. So if you look at the different mean temperatures here, we were cold, we got warmer, and now each decade from the 1980s to 90s to 2000, and also now we are ending 2020, so even this decade from 2011 to 2020 is warmer. So even though you have ups and downs and there are some flattenings of the warming trends, this one is particularly interesting because it got a lot of attention as a global warming pause. In the middle of a rapid increase, suddenly there was a somewhat of a slowdown of the global warming rate, but it doesn't show up in the decade to decade changes. So each decade is getting warmer than the previous decade, which means the year to year variabilities are not pulling down the global mean temperatures for the whole decade. That's critical to remember. So this is an inexorable warming that's continuing. So the other big things to watch out for with the warming, of course, are how glacier masses are changing and what it means for sea level rise. We will look at sea level rise later on, especially in terms of adaptation to warming that has already happened and that we have already locked in because of the emissions that have already happened since the Industrial Revolution and so on. The two big glacier masses are, of course, in the Antarctic and over Greenland, but there are also lots of them in the Alps, in the Himalayas, and Andes and other mountains that all are being monitored, especially using this satellite called GRACE, which I'll show in the next slide. Gravity Recovery and Climate Experiment is a pair of satellites that move together, and when gravity changes because of large scale mass changes because of water withdrawal from groundwaters or glacier melts, the gravity anomaly can be determined by the relative movement of the two satellites, and that can be used to estimate mass budget changes of glaciers. Amazing satellite, right? Coarse resolution, monthly averages, but still it's incredibly useful. So this complicated figure here is showing bathymetry, which we will not bother about, and ice shelf changes in ice elevation, so 3 meter per year going down to -7 per meter, and grounded ice sheet loss is being shown as well, and temperature changes. The main thing I want to point out is that Antarctica, which is surrounded by the Southern Ocean, is a complicated place. If the ocean warms, for example, atmosphere warms, humidity in the atmosphere goes up, so some parts of Antarctica can get snowfall, whereas the others begin to lose ice elevation. Here, for example, ice shelf thickness is pretty severe in some of these West Antarctic regions, Ross Sea, and so on. But there are also regions where actually some cooling is happening, which is related to the ozone hole and the special configuration of the Southern Ocean, where winds can churn the ocean much more than in other oceans, because there is no boundary. It's like a channel. So that creates some special effects over Antarctica. Nonetheless, the news is not really that great, because if you look at cumulative change in mass since 1992, you see that there is tremendous drop in gigatons of glacier loss. It is a fairly steady loss with maybe some acceleration happening now. So there is no good news as such. Even though it's complicated, it still continues to lose ice mass. Okay. Greenland is suffering even worse because of the ocean circulation around it and the Gulf Stream we will talk about a little bit later, which brings warm tropical waters, and the ocean is warming. Arctic is warming and losing sea ice, creating problems in the wobbling of the jet stream, which allows more subtropical warm air to invade Greenland and so on. And you can see that the center here is gaining a little bit of mass, but basically the edges are going off into La La Land, and there is a strong seasonal cycle in the ice sea level rise associated with the Greenland loss here, estimated from GRACE and GRACE follow-on missions in this period. But again, the ocean warming and the ice calving, various processes by which the glaciers slide down into lower altitudes where warmer air is, accelerating the glacier melt further, is going really, really fast, with moulins, so-called moulins, forming and carving into the glacier, lubricating the base and sliding the glaciers more. So it's a real mess. The glacier loss in Greenland is a real concern, especially because if we will look again at ice albedo feedback a little bit later on, where the abrupt changes, we'll talk about it in a minute, abrupt changes associated with the warming phase of the climate in terms of glacier melt can be very fast. Building glaciers takes 100,000 years and longer, but melting glaciers can happen very rapidly, giving us abrupt climate change and massive sea level rises. So that's really something to watch out for. Okay, so I will start the paleoclimate in the next podcast, but it is related very much to glacier building and glacier loss over time. We talked about Milankovitch cycle before, so obviously glacier building and loss happens on orbital timescales. The question now is how is human activity affecting glacier loss, because these are not things that recover in human timescales. They take a long time to rebuild. So these are basically irreversible changes, and we have to watch out for tipping points where massive loss can happen very abruptly and raise sea levels by several meters, causing all sorts of problems for many countries and many coastlines.